In the previous video, we learned about the quark model of the hadrons. According to the quark model, all hadrons are composed of two or three of the six fundamental constituents called quarks. These quarks are arbitrarily named up, down, strange, charm, bottom, and top. In this second video on elementary particles, we will cover the standard model of elementary particles. But first, we must introduce an extra quantum number with three values. This new quantum number is necessary for quarks to obey the Pauli exclusion principle. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It is essential for the continuity of this channel. I hope you enjoy the video, and if you have any questions or suggestions, leave them in the comments. Before moving on to the standard model of elementary particles, let's summarize what we have studied in previous videos. Each type of lepton quark has a corresponding antiparticle. All quarks have fractions of the charge on an electron. Antiquarks have opposite signs of electric charge, baryon number, and strangeness. Leptons and quarks can have a spin of 1/2 with two different states, spin up or spin down, but the magnitude is always 1/2. When quarks combine to form a hadron, their spins can either add or subtract depending on whether the spins are aligned or unaligned. Quarks are always found in pairs or triplets with other quarks and antiquarks. The resulting particles are the hadrons. Hadrons are classified into baryons and mesons. Baryons are made up of three quarks, and mesons are made up of a quark and an antiquark. Baryons have an odd number of quarks, which are spin 1/2 particles. Therefore, baryons can have either spin 1/2 or spin 3/2. Look at the example. Mesons have an even number of quarks. Their spins always combine to form an integer. Thus, mesons are either spin 0 if the two quarks are unaligned, or spin 1 if the two quarks are aligned. Look at the example. Particles with half-integer spins are called fermions and obey the Pauli exclusion principle, which states that no two identical fermions can exist in the same place with the same quantum values. Quarks, leptons, and baryons are fermions. Integer spin particles are called bosons. Since all mesons are bosons, they are not required to obey the Pauli exclusion principle. Basically, this means we can put many mesons into the same location with the same quantum numbers. You should note that there is a strong theoretical objection to the quark model. It was observed that many particles predicted by this model and detected were composed of three quarks of the same flavor, same types. For example, the delta plus particle has a spin 3/2 and is supposed to consist of three identical U quarks with exactly the same set of quantum numbers. The omega minus particle consists of three strange quarks that are all spin up, giving a spin of 3/2. And the same happens with other observed particles. It appears that the baryon construction model was inconsistent with the Pauli exclusion principle. The solution to the exclusion principle dilemma came in 1964 from the physicist Greenberg,
who postulated that each quark flavor came in three varieties, which are whimsically called colors in addition to their other properties. The color charge of a quark has three possible values: red, green, and blue. Thus, a red quark would carry 1 unit of redness, 0 blueness, and 0 greenness. Its antiparticle carries -1 unit of redness, and so on. To make a baryon, we simply take one quark of each color, and then the three up quarks in delta plus particle are no longer identical. One's red, one's green, and one's blue. Likewise, with the omega minus particle, the three strange quarks are no longer identical. One's red, one's green, and one's blue. Quarks have another property called color or color charge, and this color is necessary to satisfy the Pauli exclusion principle. The colors assigned to the flavors of quarks are the three primary colors: red, green, and blue. Color has nothing whatever to do with real color, but provides three distinct quantum states. Thus, a red quark would carry 1 unit of redness, 0 blueness, and 0 greenness. Its antiparticle carries -1 unit of redness, and so on. To make a baryon, we simply take one quark of each color, and it would serve to distinguish them and allow the exclusion principle to hold. The reason colors used is that the properties of a quark are analogous to the three primary colors. Just as different colors of light can be combined to create white, different colors of quark may be combined to construct a particle colorless. It is observed that all quark combinations that are found in nature are colorless. In other words, all naturally occurring particles are colorless, and the term colorless means that the total amount of color, that is, the sum of the color quantum numbers, is zero. This rule explains why you can make a particle out of two quarks or four quarks, and for that matter, why individual quarks do not occur in nature. The only colorless combinations you can make are quark, antiquark, quark, 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 and antiquark, antiquark, and antiquark, the antibaryons. Each quark is assumed to carry a color charge, analogous to an electric charge, and the strong force between quarks is often called the color force. The color force is carried by massless particles, bosons, called gluons. Each gluon is bicolored, carrying 1 unit of a color charge and one of an anticolor charge that allows it to transmit color when exchanged. So when a quark emits or absorbs a gluon, its color changes. The figure below illustrates the gluon exchange process inside the baryon. A baryon with 3 quarks, red, green, blue, before a color change. The gluons are represented as circles, with the color charge in the center and the anticolor charge on the outside. The blue quark emits a blue anti-green gluon, and the blue quark becomes a green quark. Green quark has absorbed the blue anti-green gluon and is now blue. The red quark emits a red anti-blue gluon, and the red quark becomes a blue quark. The blue quark has absorbed the red anti-blue gluon and is now red. The color of an individual quark changes continually as gluons are exchanged. The gluon exchange process changes the colors of the quarks in such a way that there is always one quark of each color in every baryon. Therefore, color is conserved during the emission and absorption of a gluon by a quark. Similar processes occur in mesons. The quark-antiquark pairs of mesons have cancelling color and anticolor. Suppose a meson initially consists of a green quark and an anti-green quark. The green quark emits a green anti-red gluon, changing to a red quark. The gluon is absorbed by the anti-green antiquark, which becomes an anti-red antiquark. Such changes occur continually. We can illustrate the gluon exchange by using Feynman diagrams. Suppose inside a baryon there is one up red quark that emits a red anti-green gluon, and the up red quark becomes a green quark. The down green quark has absorbed red anti-green gluon and is now a down red. Suppose inside a meson there is a down green quark and a down anti-green antiquark. The down green quark emits a green anti-red gluon, changing to a down red quark. The gluon is absorbed by the anti-green antiquark, which becomes a down anti-red antiquark. The flavor quarks change color due to gluon exchange, and gluon exchange does not change the quark flavor. You might be asking right now, can you observe a quark? The answer is no, we cannot. So you'll be wondering, how can one be so confident of the quark model when no one has ever seen an isolated quark? Well, let's see what would happen if we try to see a single quark with color by reaching deep inside a hadron and extracting a single quark. The graph illustrates the behavior of the color force between two quarks. At short distance, about 0.3 Fermi, the force between quarks is very weak. On the other hand, at larger distance, about 1 Fermi, the force between quarks is very large. The reason why an individual quark has never been observed is the enormous amount of energy that would be needed to rip it from within a hadron. The energy required to produce a separation far exceeds the pair production energy of a quark-antiquark pair. So when a large amount of energy is added to a quark system, such as a nucleon, a quark-antiquark pair is created, and the original quarks remain confined within the original system. This phenomenon is called quark confinement. Free quarks can never be seen in isolation because the color force has the interesting property that as two quarks approach each other very closely, the force between them becomes small. The result is that inside the hadron, the quarks move more or less as free particles, and this is known as asymptotic freedom. On the other hand, if the quarks move apart, the force of attraction becomes stronger. At distances that are comparable to the size of a proton, quarks are held together very strongly, and the energy required to pull one of the quarks out far exceeds the pair production energy of a quark-antiquark pair. So instead of pulling out an isolated quark, we produce mesons as the produced quark-antiquark pairs combine. The phenomenon is called quark confinement. In the 1960s was developed a theory that unifies the weak and electromagnetic forces. The weak interaction is mediated by three massive bosons, and since a large mass means a short lifetime, the exchange particles can only travel a short distance. The electromagnetic force is mediated by one massless boson and long range at sufficiently high energies. However, these particles are essentially identical and the distinction disappears, and the two electromagnetic force and weak force merge into a single interaction. But at low energies, the difference in mass between the photons and the weak bosons must be taken into account, and this makes the separation of the electromagnetic interaction and the weak interaction. This behavior during the transition from high to low energies, called symmetry breaking, doesn't answer the question of why the W and Z have large masses rather than being massless like the photon. Peter Higgs and others in 1964 used Electroweak theory to suggest an explanation by means of a Higgs field and its particle, the Higgs boson. By interacting with the Higgs field, that particles acquire their masses. During the transition from high to low energies, the Higgs boson interacts with the W and Z to slow them down. In being forced to go slower than the speed of light, they would have to have mass. The Higgs field is thought to permeate the vacuum and to confer mass on particles that now have mass by slowing them down. The Standard Model is the name given in the 1970s to a theory of fundamental particles and how they interact. This theory is a combination of the Electroweak theory and quantum chromodynamics. The Standard Model categorizes all of particles of nature in the same way that the periodic table categorizes the elements. The theory is called the Standard Model because it is so successful it has become standard. Although the details of the Standard Model are complex, their essential ingredients can be summarized as follows. In this model, all matter is made of two types of particles, quarks and leptons. For every kind of matter particle in nature, there is also an antimatter particle which has the same mass but is opposite in every other way. Quarks come in 6 flavors. It's helpful to see them as coming in pairs to make 3 generations. These are up and down, first generation, charmed and strange, second generation, and top and bottom, third generation. The second and third generations, particles, are heavier than the first generation. All stable matter in the universe is made from particles that belong to the first generation. They make protons and neutrons. The others make heavier particles that quickly decay into more stable ones. There are 6 leptons, and they are similarly arranged in 3 generations. The electron and the electron neutrino, first generation, the mu and the mu neutrino, second generation, and the tau neutrino, third generation. The muon, second generation, and tau, third generation particles are heavier than the first generation. The electron, the muon, and the tau all have an electric charge and a sizable mass. The mu and tau are very unstable to feature in ordinary matter. Neutrinos deserve a special mention because they are perhaps the least understood of all the particles in the Standard Model. They are electrically neutral, have very little mass, and interact only through the weak force, which means they pass through normal matter unimpeded and undetected. Every force in nature is due to one of the four basic interactions: strong, electromagnetic, weak, and gravitational. Three of the fundamental forces result from the exchange of force carrier particles. The force carriers are integral spin bosons, which do not obey the Pauli exclusion principle. Particles of matter transfer discrete amounts of energy by exchanging bosons with each other. Each fundamental force has its own corresponding boson, are gluons for the strong interaction among quarks, photons for the electromagnetic interaction, the W and Z particles for the weak interaction, and the graviton for the gravitational interaction. Higgs boson provides a mechanism for breaking the Electroweak symmetry and provides a logically consistent explanation of the massive nature of the W and Z bosons. According to the Standard Model, it is by interacting with the Higgs field that particles W and Z acquire their masses. I hope you understand the basics of the Standard Model. If you liked this and other videos on this channel, don't forget to share, and thank you very much.